All right, so welcome to this seminar talk. And so the speaker today is K.C. Shiva Ramanakrishnan, who's he's assistant professor at Indian Institute of Technology in Madras, Chennai, India, and he's also the CTO of the Tarides technology company. And actually, I've been working with Casey for a while on issues related to OCaml. So he's the main author of the multi-core OCaml, an extension of OCaml to shared memory concurrency, and also with algebraic effects that is now part of OCaml 5. But actually, he's here to talk about something completely different, which is his work on basically on appropriate data structures for distributed programming. Thank you, Casey.
Thanks, Xavier, for the introduction. So what I would like to do is give some context for this talk before we dive into the technical matters. So collaborative applications such as Google Docs, Figma, and Notion are quite common nowadays. And these applications allow potentially geo-distributed users to collaborate on the same project. And while these apps allow a limited form of offline access, fundamentally these apps are centralized, especially for conflict resolution. So if the user gets disconnected from the network or the network suffers a partition, then the app becomes unavailable. So here's what I find on my laptop while using Google Docs and I disconnect internet. There are two errors here, one of which is okay, but the other one is very serious. So essentially Google Docs allows you to edit documents offline, but the problem is that these sort of offline access is essentially retrofitted on top of a fundamentally centralized architecture. And what happens here is that I have multiple Google accounts on my laptop and I have enabled offline access for all of them. And I discovered while making slides for this talk that if you have multiple users, all of them with offline access enabled, then only one user is able to edit it. I mean, this is unfortunate, right? So this feature is here, but we're not able to use it. So what is the world that I would like to have? I would like to have local first software where in a disconnected network, I want users to operate on their own local versions. And when the connection is restored, you want to take these different versions and merge them together somehow, right? Resolving any conflicts that appears in these files. So the question we ask is, how do you build such applications, right? And one approach to this problem is to sort of take your fundamental data structures with which you build these applications and make them replication aware. And a well-known approach for doing this is what are known as CRDTs. CRDTs stand for conflict-free replicated data types. And the key idea here is that you replicate the state of your application at multiple replicas. CRDTs allow local operations to be performed on each of the replicas without coordination. So this is good. So you can do local operations when you're disconnected. And these updates are asynchronously shared with all of the other replicas. And the key idea here is that CRDTs are built in such a way that when you apply these asynchronous updates on all of the replicas, they all converge to the same state, right? And CRDTs are supposed to provide what is known as strong eventual consistency. So just to develop an intuition for CRDTs and to set the framework for the rest of the talk, let's look at a very simple CRDT. And the CRDT that we are going to look at is a set, but it is a set with only add and lookup operations. So this is known as a grow-only set CRDT. And the idea here is that assume that you have a set with elements 1 and 2. You would replicate the set across all of the nodes that you have. So I am simulating 2 nodes here. So each of these colored boxes represent different nodes. And you can apply local operations to these sets, right? So I can add 3 on one replica, I can add 4 on the other replica. Observe that the replica state has diverged. And what CRDTs allow you to do is to take the 2 sets and eventually merge them together. And the merge operation for sets is union, and this gives us the set 1, 2, 3, 4. And this captures the intent of what we want from a grow-only set. So this works, right? And the reason it works is because a set with only add operation and a lookup monotonically grows. This is not true if you add a remove operation, right? Let's see what goes wrong. So you have the same set, initial set with 1 and 2, and I remove the element 1 from one of the branches. And now I try to apply union. So I get the set 1 and 2, set with elements 1 and 2 back, right? So union does not work. And in particular, one way to look at this is that the effect of the remove operation has been lost, right? And this is not right. And of course, you can fix this with a different CRDT called the two-phase set. The idea itself is very simple. You represent the set with a pair of sets, one to track the additions that you performed, and another to track the removals that you performed. So we represent this as sets A and R. You look up elements in the A set after removing elements from the R set, and merge is a pairwise union of A and R sets. So let's try to do the same remove operation again. So we have the set with, so the state of the set is a pair of sets with 1 and 2 and an empty set. Just by looking at the set, you can see that there has been 2 additions performed so far, but no removals. And when you apply the remove operation, you add the element that is being removed to the remove set. And the merge is a pairwise union, so you get the set of pairs with 1, 2, and 1. And when you look up the element 1 in this set, because 1 is present in the remove set, the lookup operation returns false. Right? This works. Now we've added remove operation to the set. But there are several observations that we can make on this two-phase set. Firstly, what we've done here is to make the state of the two-phase set grow monotonically by simulating removes with additions. And the two-phase set is said to have what is known as remove wins semantics. And the idea here is that in the presence of concurrent add and remove of the same operation, it is as if the remove operation wins, right? So when you merge these, the remove operation will take effect and the added element will not be there. But there are several downsides to constructing replicated data types using this approach. Firstly, we've had to sort of re-engineer the set implementation in order to allow for a remove operation. Secondly, removed elements always are there in the remove set. These are known as tombstones. They actually represent the fact that something has been removed. And these tombstones cannot be erased away, right? You have to keep these tombstones around. And once you remove an element from this set, you can never add it back because the tombstones are never gone. So based on this one simple example, you can sort of step back and generalize the challenges with CRDTs. Essentially, monotonicity forces re-engineering of data structures from scratch. Right? This was easy for two-phase set, but for more complicated data structures, you have to be very ingenious. Right? And this challenges proving the correctness of even sequential operations right on these data structures. Secondly, CRDTs, when compared to their sequential counterparts, are less time and space efficient. In the case of two-phase set, we have these tombstones around, so it affects the time and space efficiency of the set implementation. And thirdly, this is my pet peeve. So little attention has been paid for composition of RDTs. So when I program in OCaml, I might have an alpha set, I might have an integer, I can compose them together and get an integer set. But when you think about CRDTs, they're all built as a one-off data structure. So there's no easy way to say, hey, here's an alpha set, here's a counter CRDT. I want to put them together to get a counter set CRDT, right? It's not been approached that way, and this is a big problem for composition and building larger applications, right? And there is also the question of whether this composition actually gives you a CRDT at all. So we want this convergence property. It is unclear whether this composition gives you that. So a few years ago, we started thinking about this problem, and we asked, can we do better? essentially, can we do it differently? And our inspiration is distributed version control systems like Git, right? If you think about Git, what Git is doing, it's very nice, right? So you have this abstraction of a sequential file system, and you add this notion of branches and merges on top. Now you have a file system that can be collaborated by users who are distributed, and they don't need to be connected at all. They can completely locally operate, and then at some later point merge their updates together, right? And the question that we asked is, can we do the same thing for data types? So just to set the stage for how we think about distributed version control systems, version control systems like Git are typically used to maintain source code. So suppose you have a main branch where you maintain your source code, and then you forked off another branch for developing your feature. In the meantime, the main branch may have had bug fixes applied to it. So you have a few more commits on the main branch. And eventually, when the feature is ready, you're going to take these two branches, essentially these two commits, and merge them together. So in Git, this happens to be a three-way merge. So you are given three versions to merge, the two divergent versions that you're merging, but you also get something interesting, which is the lowest common ancestor state, which captures the causal history. It's the point at which the two versions diverged, right? And this happens to be quite useful for Git. It is not exploited all the time, but it turns out that this is fundamental for how we think about data types. So in Git, this might give you a successful merge, in which case the merge has the effect of both of the branches, or you may have conflicts, in which case Git presents it to the programmer. They will have to fix the conflicts to give a sensible merge. So mergeable replicated data types, what we are proposing, essentially lifts data types and makes them aware of this merges, right? So one way to think about it is you have Git. I'm going to store arbitrary data types in Git rather than just text files, right? And in our world, the branches that you have in Git represents the state of replicas which can independently evolve, right? That's the intuition that you should have. So how do you build a replicated data type? The promise is that you can take any sequential data type, you give this three-way merge function that is specific to that particular data type, that captures all the details of how the distribution, right? Any sort of details of the distribution can be pushed into this three-way merge, and what you get is a replicated data type, right? This is the promise. So let's see how this works. In distributed systems, I think there's a common joke that we start with counter all the time, and I would like to keep on that tradition and start with a counter. So we have a counter mergeable replicated data type. So the interface and the implementation is given here. This is the entire implementation, and this is given as a OCaml signature and its implementation. This counter supports add, multiply, and read operations, and add and multiply take the value of the counter, the value to add the counter with or to multiply it with, and what you expect to return is the new value of the counter, right? And we also have this merge function that takes three arguments, the lowest common ancestor value and the two versions. And the merge is defined as the sum of the lowest common ancestor value and the difference between the lowest common ancestor and the two versions, right? It's essentially the delta between the lowest common ancestor and the two versions that you have. Let's see how this works with an example. So suppose the initial value of the counter is 7. You add 1 to it, you get the counter 8. You can multiply the counter value by 3, you get 21. The effect of these changes is to add 1 and 14 to the branches. And eventually at some point you're going to take these branches and merge them. And at that point we apply this three-way merge, right? And what this does is it adds 7 and the two deltas, 1 and 14 together, you get 22. This is the intended behavior of what we were trying to do, right? And you also get the same result on the other side as well. So these counters merge. Okay, so this is fine. Does this actually generalize to more complicated data types? So here is a set MRDT. And the interesting bit is this is the merge function for any set, right? I don't care about your sequential implementation. This is your merge function, right? So the merge function says, I take 3 versions, the lowest common ancestor version 1 and version 2. The merge of these sets is given by the union of the common elements that were present in all the 3 versions and the elements that have been added in version 1 and version 2 since the LCA. If you sort of squint, right, this is isomorphic to the counter merge that we were doing. So you had this initial value and the 2 deltas, which is exactly what we are doing. It turns out this pattern reappears for every data type. So you compute some common aspects and then the 2 deltas and you sort of merge them together in a data structure specific way, right? So let's apply this merge function to the problematic example that we had earlier, which is this remove example where the effect of the remove was lost. So in the case of MRDTs, the equivalent execution would be our initial state is 1, 2. We did not do any operations on the left, so it still remains 1, 2. And on the right, we remove the element, so we get 2. So the question we ask is, hey, what is the value of the merge? So the LCA version 1 and version 2 are annotated here. And when you apply the merge function, you can see that the common elements between the 3 versions is 2. No elements have been added to the left or the right compared to the LCA. So the result is 2. And this captures what we want to capture with the idea of a remove. There are several nice things going on here compared to the CRDT implementation earlier. Observe that we are supporting removes, but there are no tombstones. Local operations are efficient because they are plain sequential implementations of sets. And removed elements can be added back as well, right? So just to show how that works, we start with the state that we had in the last slide, and we are going to add the element 1 back, which we had just removed earlier. So this gives us set 1 and 2. And now let's try to merge these sets together. So at this point in merge, the LCA version 1 and version 2 are described here. And if you look at the common elements, it is 2. On the left, we haven't added any elements, but on the right, we have 1 added compared to the LCA. So now we have 1 and 2. So this also works, right? Removed elements can be added back. Okay, this is all very nice, right? So this works very well. But the question that should pop up in your head is, how does MRDTs get away with having no tombstones at all, right? Where CRDTs had tombstones, and what's the secret sauce? So if you think about what tombstones are representing in CRDTs, they are sort of capturing this history, right? When you remove an element and you add a tombstone, you are essentially saying at some point in the history, remove happened. In MRDTs, Git records the causal history for us, right? And Git is sort of the underlying Git data structure or Git application on top of which we are running this records the causal history, and it is given to the data structure in the form of the lowest common ancestor as part of the 3-way merge, right? And that is doing the work for us. And again, the next question that you should ask is, hey, how does Git actually keep track of causal history efficiently? And here is where persistent data structures come in. So before we dive in, we should talk a little bit about how Git actually stores the objects. So abstractly, Git store can be split into 2 different stores, a tag store and a block store. A tag store, as the name represents, stores Git tags, but it also stores identifiers for the branches. And that is the only mutable part of Git. The block store does the heavy lifting for you. It stores all the files under version control. And block store is special. So it is an immutable store. It is append only, and it is content addressed. Right? And the way to think about the block store is that it's a key value store where the keys are hashes of the objects and the values are objects themselves. Right? So the block store stores different kinds of objects. It has commit objects that represent Git commits. It has tree objects that represent the directory structure of the file system that is under Git. And it has blob objects that are leaves in this tree. And these are essentially our files that we store under Git. Every tag uniquely points to a commit. The commit object may point to one or more other commit objects, but it also uniquely points to a tree object that refers to the top level directory of the file system under Git. And the tree object, as the name suggests, might point to several other tree objects or several other blob objects. Okay, so that's fine. So let's actually look at where this persistence is exploited, right? So suppose so it is exploited in the block store. So let's work through an example. Suppose you initialize an empty Git repository and you add a file. I'm going to add a file test.txt at the top level directory, and I want to see how the block store evolves. So when you commit this, you're going to have several objects added. You're going to have a commit object that refers to the tree object, which in turn refers to the blob object that corresponds to the file test.txt. And the important thing to note here is that all of the edges that I've drawn here are actually represented by hashes in the objects because our store is content addressed. So this gives us a nice property. So if one of the objects gets corrupted, its hash changes, and it's because the hash changes, all of the hashes that go up the spine also change. So you can quickly verify the integrity of the Git store. Right? It's a nice property that you get as an offshoot of what we are doing here. So let's get back to editing this particular Git repository. Let's say we are going to now add a file called new.txt, and we are modifying test.txt, and we commit this change. So you get a second commit, which points to the first commit. You get a new tree object, and then the tree object points to two other blob objects, which refers to the file. Right? So the file is different. So between test.txt in the first version and the second version, you have two different blobs. This is fine. Nothing interesting is happening so far. But now, let's say you wanted to restore the original test.txt under a directory called BAK on your top level directory, right? So now I commit this change. What's going to happen? I'm going to also have a third commit, which points to the second commit. I'm going to have a new tree object. But things start getting interesting again now. So between the second commit and the third commit, the files new.txt and test.txt in the top level directory haven't changed. So because our store is content addressed, we share those blob objects. And something more interesting happens. Observe that the content of the top level directory in the first commit is the same as the content of the back directory in the third commit. So the back pointer actually points back to the tree node that you have in the first commit. So this is wonderful, right? This is how Git keeps track of history efficiently. So if you have a huge file system and you modify one of the objects, files, of course, you're going to modify all the way up the chain because your hashes will change. But a lot of things are actually shared between different commits. And that's what makes Git efficient. Right? And here is how persistent data structures ensure that Git can actually store things very efficiently. Okay. So in our work, we don't directly store objects in a Git store, but we store it in a distributed database called Ermin, which is built on the principles of Git. Right? It's an OCaml database, and what Ermin gives us access to is that you can store arbitrary OCaml data types in Ermin, and whenever you perform this merge, it calls back the three-way merge function in order to compute the merge of these two versions that you might have. So compared to Git, Ermin adds one other extra feature, which is that blob objects can point to other blob objects. And the way to sort of think about this is that is our heap into which we store all of our rich data structures. So we've created several mergeable persistent data structures, including stacks, queues, ropes, balanced binary trees, and so on. And more details about this is found in our OOPSLA 2019 paper, where we introduce mergeable replicated data types. Okay, so the next thing that I want to say is a little bit about the commit objects. The commit objects in the Git store form a DAG, a directed acyclic graph. And this directed acyclic graph captures the causal history of how the state of the store came to be, right? And if you sort of turn this into the distributed systems parlance, this is essentially happens before relation. So the causal history is capturing happens before. And hence, MRDTs provide causal consistency to your changes. And causal consistency is the strongest consistency level that you can achieve without coordination between different replicas. And the runtime manifestation of this commit DAG is very important because given two versions that we want to merge, we actually traverse this DAG to find the lowest common ancestor. Okay, so Git remembers the entire history by default, right? So all the way from the initial commit to your current versions, it remembers everything. This is a very useful form of provenance. So in Git, if you wanted to know how a particular change in a file came to be, you can keep traversing the history to find out where it was added. But what we are usually building is a distributed database, right? Where provenance might not be something that we want. So if we don't care about provenance, keeping the entire history is wasteful. So your nodes in the distributed database will quickly run out of memory, right? And it wouldn't be a practical one. But history is needed for the lowest common ancestor computation, right? So the question is, how much history should we keep for our MRDTs? It turns out that if you have the constraint that there is a fixed number of replicas that you have in your system, then you can find a nice answer. The answer is that any commits that are older than the latest commit k that is known by all of the replicas can be garbage collected, right? And the way to sort of think about this is this commit k is on every replica. So you can sort of imagine this commit k as the initial state from which all of the different divergence happened, right? So if you ask for the LCA, you would never ask for a commit which is older than this k. And when I say the older commits can be GC'd, the commits and the tree nodes and everything else that it points to can also be garbage collected away. Okay. So we implemented a distributed programming model on top of this idea in a paper called Banyan, which provides you this model and also talks about the garbage collector. Yeah, more details of this is actually found in my student's master's thesis. Okay, hopefully so far I've given you, hopefully I've convinced you that MRDTs are a useful technique for constructing replicated data types by taking sequential data types and encapsulating the details of the distribution in a three-way merge. So the question that we next ask is, does this actually make proving the correctness of MRDTs easier, right? And what do I mean by this? So one question that you might ask is, hey, you gave me a set MRDT, right? And does this actually have the add-wins semantics? What is an add-wins semantics? When you have a concurrent add and remove of the same element, you treat it as if the add operation wins. So the element is present in the merge, right? And this is also known as observed removed set in the CRDT parlance. So I might interchangeably use it in the rest of the slides. So I am reproducing the same merge function as before. So let's check whether our set is an add wins set. So consider that initially the set is singleton set 1. You add the element 1. 1 is already present in the set, so the set state doesn't change. But you remove it on the other side, so it becomes an empty set. According to the definition of add wins set, there is a concurrent add and remove of the same operation. So we would expect that this element 1 be present in the merge. But that's not true, because if you apply our merge function, you will see that the common elements is an empty set. There have been no elements that have been added to the left or right compared to the LCA, so we get an empty set here. And the problem here to point out is that when we perform this add on the left-hand side, we actually forgot the fact that an addition was performed, right? So that's the problematic thing here. So our set is not an add-win set. That's okay, right? But the important point that I want you to focus on is that the sets have in fact converged, right? So just checking for convergence of the merge function is alone not sufficient, right? You want to do something more. You want to capture the intent of what you are trying to do, right? So how do you concretize intent? So we need a formal specification language to capture the intent of what we mean by MRDTs, what we want from MRDTs, and the specification language must be rich enough to capture the details of distributed execution. So it turns out that even simple data structures attract enormous complexity when made distributed. Lindsay Cooper is a distributed systems researcher. She does distributed systems verification for a living, and she joked that like even implementing and reasoning about counters in a distributed system gets really complicated. Right? And this is true. So far, we've only seen counters and sets. We have not seen anything more, right? So we believe that we need mechanization to bridge the gap between the specification and the implementation. So we have this framework called PEOPLE, which is a framework for implementing and proving MRDTs. It is implemented as an F-star library. F-star is a programming language. It is a programming language where you can also do proofs. And a good thing about F-star is that it can discharge the verification conditions through an SMT solver underneath. So you can use Z3 to discharge the proof obligations. So our specification language is based on this POPL 2014 work by Burkhardt on replicated data types. So we develop a replication-aware simulation relation in order to connect the specification with the implementation. Oops, sorry. So we have also proved a large number of space and time efficient MRDTs correct using this framework. And in particular, we have a first certified implementation of a replicated queue that has constant time push and pop and a linear time merge. So we've also show how to compose MRDTs and their proofs. I'll come back to this later. And F-star is a language from which you can extract OCaml code. So our extracted OCaml RDTs are compatible with Ermin, our distributed database which I've shown earlier. Okay, let's fix our set to become an advent set. And the idea is that the problem was that we did not discriminate duplicate additions. And you can do that by associating a unique ID. So let's say our initial state of the set is a, 1, where a is the element and 1 is the unique ID. When you do an addition again, we pick a new unique ID 2, and then we add the element a, 2 to the set. Now we remember that the addition has happened. Remove operation has to remove all the occurrences of a element from the set. So here there is 1, it removes it, and you get an empty set. So now when you apply the three-way merge, you can see that the common element is empty, but we have added the element a, 2 to the left-hand side, and on the right it's still empty set. So the element a, 2 survives in the final set, which captures the intent of what is going on with the advent set. Okay, so how do we represent MRDTs in our framework? The MRDTs are plain, purely functional data structures, right? So there is nothing interesting happening here. So here's a specification of the implementation of the two-phase set in our framework. So there are 6 lines here, and the first one says that the state of the set is represented by a set of pairs of element and the IDs. For simplicity, we are assuming that the elements are natural numbers as well. Initial state is an empty set. We have these do functions that tell you how to apply local operations on the state. And the merge function is our merge, and this is exactly the same as what I had shown earlier. So one thing to note here is that we assume that the runtime system gives you access to a unique Lamport timestamp for every operation, right? And this unique Lamport timestamp can be produced completely locally. These are not, you don't need coordination to produce these, so you can locally do it very fast. And we use this operation for whenever we need uniqueness or we need causality between operations, right? So let's look at, say, add in detail. What does add say? Add says that if you want to add an element A to the concrete set sigma with the timestamp t, do operations are supposed to return a pair of results, the new state of the set and the return value of the operation. So the new state of the set is the old state with this new element a comma t, and the element and the result of addition is uninteresting, so we return bottom. And remove operation here says that when you remove the element a from this concrete set sigma with the timestamp t, you get a new state back where no element has the first component to be a, right, which is walking through the entire set and removing all the elements with the first component to be a. And it doesn't return anything interesting, so you get bottom as a result. Okay, all of our implementations sort of follow the same procedure, right? Our specifications are a little bit more interesting. So these specifications are event based. If you are aware of the specifications that are used in relaxed memory models, they are very similar here. So you have a set of events E, and you have functions oper, rval, and time, which return the operation, the return value, and the timestamp associated with that event. And you have a visibility relation, which is an irreflexive transitive relation that captures the happens before relation between different events, right? So I have shown an abstract execution on the right, which corresponds to the concrete execution that we had seen in the previous slide. So what is happening here? On the right, we have operations add and remove, right? And we also have this visibility edges that correspond to which events were visible to which other events, right? And what is the specification going to say? The specification is essentially going to say, given the abstract execution on the right, what should the read operation return, right? That is what the specification is trying to say. And the specification is written below. It says that when you perform a read on an abstract execution, you get a set of all A's such that there exists an event E whose operation is add of A, and there does not exist an event F whose operation is remove of A, and F happen to witness E, right? So you are essentially saying any add operation that has been witnessed by a remove will not contribute to the final result, right? And let's look at how this works in the execution on the right. The add in the blue box has been seen by this remove, yellow box, which is also seen by this read. So the blue add does not contribute to the result, but this add in the green box has not seen by a remove, right? So that result is contributed to the final result, so you get the singleton set A. Right? Okay, this is how we describe our specifications. So we need a simulation relation. I won't say much about the simulation relation, but simulation relation connects the abstract and the concrete states. For the add-win set, the simulation relation is given here. It connects the abstract execution I with the concrete state sigma. And what does it say? It says for every pair A comma T that you have in the concrete state, it better be the case that in the abstract execution I, there was an operation E, which was an add of A with the same timestamp T, and there does not exist an event F with the operation remove of A, and E is visible to F, right? We are simply restating the specification again, right? And what we observe in more complicated data types is that with the complexity of the data types, the simulation relation also gets more complicated, right? And this is an obligation that we place on the developer, right? They have to write the simulation relation. So the main verification effort is to show that the above relation is indeed a simulation relation. This is shown separately for the operations and the merge function, and the proof is by induction on the execution trace. So the simulation relation for operations is very standard. So given an abstract execution I and a concrete execution sigma, which is related by the simulation relation, if you apply some operation on the concrete state to get sigma prime, and you apply the the abstract operation on I, you get this I prime. You need to show that they are still related by the simulation relation. This is fairly standard, right? If you've done simulation proofs, this is what you will do. Merge function verification is a little bit more funky. Oops. So the highlighted portion here is basically our concrete merge, right? So there is a sigma LCA, sigma A, sigma B, LCA A and B versions, and the merge function simply computes the concrete merge. And assuming that these concrete states are related to abstract states, we also have a definition for the abstract merge, right? And if you sort of think about it, the abstract merge is very simple, right? So we have a set of events and some relations. So the merge is just the union of these sets and relations. So they are defined once and for all of the data types that you want to define. And the obligation is to show that the concrete merge is indeed related by the simulation relation to the abstract merge, right? And there are some other well-formedness condition which I am not going to go into. So using this technique, we verified a large number of MRDTs, which are very common in CRDT literature. So the OR set highlighted here is our add-wins set. F-star is a solver-aided programming language, right? So you can offload all of the verification conditions to the solver. It tries to churn through and try to compute, verify that these conditions are in fact valid, or it times out, right? You can also do extrinsic proofs in F-star where you explicitly provide lemmas to help the solver. So what I've shown here on the lines of proof and lemmas is that you can add more lemmas to help the solver to help the solver, and the verification time comes down, right? By verification here, think of type checking, right? F-star has a program, you're type checking that program. It used to take 43 seconds, it comes down to 8 seconds. So you can pay as you go, right? So we have also implemented more efficient versions of our add-wins set. So the way we discriminated duplicate additions is by adding duplicate elements. You can also do something interesting where you don't keep the original element and only keep the new one, because the Lamport timestamps always increase. So this is a little bit more complicated. Essentially what it allows you to do is to remove duplicates, right? That is done. That is the OR set space, and OR set space time is uses a balanced binary search tree in order to implement the set. And the number of lines of code is 97 and the number of lines of proof is 266, which I think is still reasonable, right? Okay, so in the rest of the talk, I would like to talk about the problem of composition. So Martin Kleppmann is again another distributed systems researcher. He does verification of CRDTs for a living. He's also an old hand at distributed systems. He's written this wonderful book on practical distributed systems. So he tweeted some time ago where he said he wrote down this very simple CRDT algorithm that he thought was obviously correct for a course that he was teaching. It was only 10 lines or so. And then after hours of trying to prove this code right, he found a fatal bug, right? And it turns out that this bug only occurs during the composition of two individually correct CRDTs, right? If this is so difficult for Martin Kleppmann, I wouldn't give it to a developer who just wants to get things done. So I think composition is hard. We have to make it easier. So in people, we show how to build composable MRDTs, right? And we sort of show how to do this with a simple application. So imagine that you want to build a simple IRC style chat, right? Group chat, where you can send and receive messages on different channels, right? And the state of the application is represented by a map MRDT, where the keys are strings, channel names, and the values are mergeable logs MRDT. So what is a mergeable log? mergeable log is just a usual log where you can append messages, but it also keeps track of the timestamp, so that if I give you 2 logs, you can order them according to the timestamps, right? So you have 2 MRDTs here, and our goal is to prove the map and the log separately and to compose them together and use the proof of the underlying RDTs to prove the correctness of the chat application. Right? So the implementation and the specification simulation relation of the map MRDT is given here. It's a bit complicated, but I don't want you to focus on the details. Right? The state of the map itself is represented by a set of pairs of strings and values. The values are themselves MRDTs here. That's the first observation. The second observation is that the merge function of the map appeals to the merge function of the underlying type. And thirdly, because we are also doing proofs and not just implementations, the simulation relation that you want to write for the map appeals to the simulation relation of the underlying value type. Right? I will let you ponder about the details of this later, but that's all it is, right? And with this, we have constructed the IRC chat application state by instantiating this generic map with the mergeable log, and the proof of correctness automatically falls out, right? So you don't have to do anything more than what you would have done in, say, OCaml. You just put them together, and this one comes out. So the details of this can be found in our PLDI 2022 paper, where we show how to build certified MRDTs. So where do we go from here? I've told you all of the nice things, but there is this particular queue implementation which I'm not at all happy with. So the queue is lines of code is 32 lines, but the lines of proof is 1100. Right? It's too big, and we need 75 LMS, and the type checking takes more than an hour. I sometimes wonder why my graduate student waited for an hour thinking that it will finish, but I mean, maybe she left it run overnight. The problem is this, right? Queue MRDT is actually quite simple to implement. It's your standard two-list queue, right, that we've studied, and there is a merge function, right? This works. And the thing that we need to do is to provide semantics for what happens when you dequeue an element on 2 different replicas, right? And the standard way distributed queues handle this is at least one semantics, right? So a given element may be dequeued multiple times at multiple replicas, and that's all it is. And in our queue, given you want to enqueue E, we enqueue the pair E comma T, where T is the unique Lamport timestamp. This is to enable our merge function to work well. So here is a sample execution of how this works. Timestamp are not shown for simplicity. Instead of timestamps, I'm assuming that all the elements are unique and they are ordered, right? This is what is given by Lamport timestamps as well. So initial state of the queue has 5 elements, 1, 2, 3, 4, 5. I dequeue an element, and then I enqueue 8 and 9. So I dequeue 1, and I push 8 and 9 to the queue to get 2, 3, 4, 5, 8, 9. On the right, I dequeue 2 elements, 1 and 2, and I enqueue 6 and 7. So I get 3, 4, 5, 6, 7. Observe that the element 1 has been dequeued on both sides, right? It shouldn't be present in the final merged queue. And 2 has been dequeued as well. So when I merge it, 2 should also not appear, right? How do I define this merge function? It is very simple. Again, same thing as what we had seen earlier, right? What are the common elements between the 3 versions? In particular, common here means the longest common contiguous subsequence that forms the prefix of the queue. And then you take the delta, the difference between the lowest common ancestor in the 2 versions. So the elements that have been pushed, right? 8, 9, and 6, 7. And because we have these Lamport timestamps which capture the order in which these operations are performed, you can just merge them based on the Lamport timestamps, and you will get a suffix which preserves the individual orders on each of the queues, as well as merging them in a consistent order. You want convergence as well, right? You cannot leave things to chance. So we want a deterministic merge there, which is given by the Lamport timestamp. So this is wonderful, right? This is why it's only 32 lines of code, but the specification is incredibly complicated. And the reason it is complicated is because we are trying to describe what a queue is based on these very loosely defined event-based structures which capture these partially ordered visibility relations, right? And the thing is, the complexity here is not because of distribution alone. It is because we don't have the inductive structure of what it means to be a list, right? You have to reconstruct the fact that there is an order in the element by doing complicated operations. And I have no confidence that any practical programmer will be able to write this, right? This is not what we want to actually do, right? And specifications are very hard, simulation relations are harder. Now you need to relate the operation here with the implementation, which is simple. I don't think this is the approach that we should go towards, right? So of course, when I'm saying all this, I am working on a better specification language. The intuition is this, right? The thing that actually works very well is that I understand the sequential implementation very well. I know how a queue works. Why don't I take that as the sequential specification, and I want to do something about the operations that I perform across the different replicas. For this, I need a way to constrain the operations. And what are these constraints? The constraints could be, if you have two operations that are concurrent, order them this way, or certain operations can commute. And I also need other properties like deduplication. So in queues, we have two dequeue operations, but if you linearize this, you only consume one element. So we need some other properties there. And the way we want to actually think about the MRDT behavior is that you take the sequential data type, you take all the operations that you have performed, you linearize them according to the constraints that you have described for the particular data type. And every observable behavior of MRDTs should match the constrained trace applied to the sequential data type, right? So that's the goal here. And here is an example of the ordering property, how you would describe it. For an add wins set, how do we describe add wins? If you have a concurrent add and remove, you can order the remove before add, right? So that the add actually wins. And that is what the first line is saying. Rest of it is not important, right? So that's an ordering constraint that we have. We are again doing this in F-star. F-star has a nice automation framework. So the hope is that you will describe the sequential data type, you will describe the constraints, you will describe your implementation of the MRDT, and we will be able to automatically tell you whether the observable behavior of the MRDT is matching the constrained linearization of the traces applied to sequential data types. Still work in progress, right? So I don't think I want to say more about this. But to summarize, yeah, MRDTs simplify the construction of replicated data types by taking sequential data types and encapsulating the details in this three-way merge function. The reason why MRDTs make it simple to program and also efficient is because of persistent data structures that are at play in Git. And we believe that the three-way merge functions is a pathway to verifying MRDTs. So I would like to stop here, and thanks for listening. I'm happy to take any questions.